to this computer, and then let me see if I can share. Oh yeah, this looks, I feel, a lot better than what we had dealt with in the past. Where's my... Uh-huh. Yes, much better. And then where can I hide this? Here we go. Okay, so kind of the idea for today, and I can also tell you about what my plan is. Sorry about that. Oh my God. I can tell you about the plan for the next coming weeks. So, or next coming days. So for today, I'll tell you a little bit about the kind of like the continuous version of the singular value decomposition. It's an interesting topic and it's also convenient to know about later on. This is called like the Schmidt decomposition in quantum mechanics. So I'll tell you about that today. Maybe I'll start a little bit of probability, but if I don't, like next week, we'll focus on probability. I'll see how you can use some ideas of the SVD stuff on probability theory for like joint random variables. And that's also useful because for like kind of like the pet project we'll talk about later on, with these like sequences of strings of like binary sequences of zeros and ones that I had told you about. We do need to know probability theory eventually. And once we're done with those things, that kind of like wraps up all the SVD part. And then we kind of move into how do you apply the SVD to tensors, like of higher order. And that's called like the tensor network, tensor trains, tensor train decomposition and other stuff. Which is one of the other things that we would like to understand in the class. Okay. But yeah, I've thought like it was better to just to kind of like do everything first related to SVD so that that's kind of like out of the way. And then we'll kind of like, once you know SVD really well, then the like the application to the tensors is a little bit more like straightforward. Um, so I'll call this like SVD in the continuous case. And again, like usually that goes under the name of the Schmidt decomposition. Um, in quantum mechanics, that's what they call it. So I will be a little bit more like formal, which is the name that you give when you don't, you kind of like put some technicalities under the rug. So I'll kind of like tell you kind of like the broad picture of how things are supposed to work. But yeah, you, in order to fill in the details, like and be 100% accurate, that's a little bit more tedious and like, orthogonal to what we're interested, just like to see how the idea is supposed to play out. So one of the things is that, which is something I had mentioned before, is that um, you can kind of like talk about when you have functions, you can kind of define a dot product between four functions, which is not called like a dot product, it's just called like an inner product. So for today, kind of like the functions I'll work with, they are like periodic functions. That kind of like does make whatever I say a little bit more accurate. So my functions will be periodic functions. On the interval negative pi pi, just to make of, so they have period to pi, of period to pi. So like I'll think about them as like a function from negative pi pi into the reals. And because they're periodic, f of negative pi is the same as f of pi. So many of these, like like sine, cosine, like some of these functions are like sine of x, cosine of x, also. But also like of higher frequencies, right? Like sine of 3x also satisfies that condition. I mean, these have like, shorter period, but they kind of like, but periodic, I just mean that f of negative pi equals f of pi. It doesn't matter whether like the period itself is actually shorter than that. That at least when you get at the endpoint state, the value is like big. Uh, so you can kind of like define a set, which is like all these periodic functions. Okay, so I'll just call it f, or like I'll just call it func. All these periodic functions. Well, it's extra condition, like for example, just to make the right people, you could ask functions without the data, which are also differentiable. Okay, just to make your life easier. Even if you wanted, you can ask for something better, which are smooth. Like again, it's not necessary or anything like that, but just to make your life easier. How it is possible. So smooth just means that it has something very, very limited. So if you have two functions, you can define their inner product, right? Which we have talked about that. So let's look at inner product and functions. So I'll use kind of like this Dirac notation, which is like just to some extent, where like if you call f and g the functions. So if f and g are two functions, their dot product, I'll write it like this, and it's just like the integral from negative pi to pi of f of x times g of x times dx. So again, like this, just to kind of like make the connection to what we had talked about before, this is kind of like a natural generalization because if you remember, I had told you, oh, you can think of a function as a vector, but with a continuous index, right? So if you thought about like, if you think of f as a vector with a continuous index, and g is a function which I'm thinking of as a vector, as a continuous index, right? Like then their dot product kind of like in a sense should be the sum of xx, gx, but because the index is continuous, you cannot really do it that way. So that's why you turn it into an integral and then kind of like, for it to kind of like, so this is not completely true, right? But in quotes, that's what you would like to do. Right. And so kind of like the replacement for doing like a continuous sum is like the integration, right? So it really is kind of like a natural generalization of like the dot product between vectors, like with a finite number of entries, like the integration of that thing. Is that okay? So far, so good, making sense. And then one thing you can, this is like, and then you can say by analogy, right, the two vectors are orthogonal if their dot product is zero, so two functions are orthogonal if their inner product is zero, right? So two functions are orthogonal if the product integrates to zero. So f and g are orthogonal. Right, and that means, again, that is that they integrate to zero, right? Okay, now here's the thing to remember. Function is even, right? What is a function? So imagine you have an even function and then, well, let's say that, okay, so I'll say that f is odd is an odd function, right? F is odd if f of negative x, right, is negative f of x, right? And I'll call g an even function if f of x, g of x equals g of negative x. So usually for today, if I'm thinking of an odd function, I'll use the letter f for it. And that's why I chose like the interval to be symmetric about the origin, so that it's a big space completely makes sense. And that's what the origin is, right? And so this is a very simple lemma, but it's not like you can think about it. Every even function is orthogonal to every odd function. So let's just think about that for a second. So here's my claim. It's like a super quick proof. If f is odd and g is even, then they are orthogonal. What would that be? So you just have to write their definition, right? What is f? The inner product of f with g. So what I'm saying is that this integral always is zero if f is odd and is even. Okay. Not my problem. Someone that is even an odd function. Even right. Yeah, like right. Wait, let's see. So is this no like wait. Well, even like okay, let's see. What is f of x times g of negative x? Right, like u is for like So f is even as sorry, f is odd, right? So this is f of a negative x. Sorry, f of and then g is even, so this is right. And then I did this correctly, right? Like so is that so that is just odd, right? Right, right, because I mean yeah, that's so confusing because it's not like even times, right? It's not like multiplication of numbers, right? Because it's like addition, right, right, right. It's right, right, right. Even oh my god, like yeah, I forgot about that. Yeah, yeah. So like the product is odd, right? That's what matters. But yeah, it's not. You should think about it more like addition, as you're saying, not like multiplication, which is kind of funny. Okay, so this is an odd function. And the integral of an odd function on a symmetric interval is 0, right? So kind of like that means that whenever you have an even function, if you think about it kind of like anything in the dimensional vector, that's perpendicular to an odd function. So all the cosines of different frequencies are orthogonal to all the sines of different frequencies, like just for free. Like you don't need to know anything else. I mean there are ways to prove that more directly. Using like the trig identities because there are all these trig formulas for the product of sines and cosines. But if you want to have like a picture, it's kind of like saying like, I mean, I won't be able to do much of a picture, but, like, for example, this is sine of x, think of it as a function, and then it's orthogonal to, it's kind of like orthogonal to cosine of x, right? And, well, the other thing that does happen, which is not coming from, which is not like from here, but, you can also prove like, the cosines like of different frequencies are also orthogonal to with each other. So actually, this looks not it's not looking more like I think thing. But at least for free, like the only of what I said, the only thing you know is that this one has to be perpendicular to cosine, and that this one has to be perpendicular to cosine. That. But then you can show the cosine and cosine to the right side of it. Yeah, maybe I will just draw so that not to confuse it with like, what I'm saying is that, yeah, this, like, actually, let me make it a bit more orthogonal so that I'll put, I know what I'll put. I'll put cosine of mx for any m integer, maybe m integer, and sine of nx. So just to say kind of like, oh yeah, it doesn't matter which one you use. Just from the fact that one is odd and the other is even, that you. It's just sort of something on, yeah. Okay. And in fact, so here's another thing. I don't like any function is a sum of an even and an odd function, right? Does that make sense? Let's write that also here. Uh, here's another claim. So this is claim one, right? Claim two. Um, let's call the function h, just to not get biased. If h is a function, h is a sum of an even and an odd function. And the proof is kind of like very simple because h of x is just h of x plus h of minus x over 2 plus h of x minus h of minus x over 2, right? You know, h over 2, that gives you back h, and then these two cancel out the h of negative x. But you can see kind of like, this is even, this part is even, right? And this part is odd. That's the same trick that you do for a matrix, right? So any matrix is the sum of a symmetric matrix. I mean, any square matrix is the sum of a symmetric matrix and a symmetric matrix, and it's the same thing with the transpose. You do a plus a transpose number 2 plus a minus a transpose number 2. So it's kind of like the same idea. Is that okay? Sorry, I'm flipping the colors because, yeah, like just to kind of go to, this is even, and this one was odd. So that kind of gives you like a nice picture for like the periodic function, because that means that that even and odd functions are two subspaces which are mutually orthogonal, and that they span the entire space of periodic functions. So essentially, like what you can. I mean, this is a misleading picture, but I'll do it anyways. So you have like the space of even periodic functions, and then you have the space of odd periodic functions. It's kind of what we were talking about last time, like with the two planes, like and then it's a bit misleading because like the idea is like I don't have enough dimensions to draw something nice, but what I'm trying to say here is like kind of like that odd periodics are all perpendicular to the even periodic functions, and then any function is a combination of odd and even. So they kind of like generate the entire. And then if you have like a random function, if you have a random function h, then it is the sum of an even and an odd. Is that okay so far? Are we doing up to any questions up to this point? Well, I mean, like the space is actually infinite dimensional, right? Right. It's for this space, right? I'm trying to pretend that this is not like 4-dimensional, right? So like there are 2 dimensions for the even ones, right? And 2 dimensions for the odd one. Because right, in 3 dimensions, this is not correct because then they overlap in a line, right? And then a line, like the idea that every vector, the only vector that's perpendicular to itself is the 0 vector, right? So that's why this is not correct in 3D. So it's more like a 4D picture quotes. I'll put it 4D in quotes No, like it's like a 4D analogy. Yes. Yeah. Thanks for like bringing that up. And that's the best I can do because if I try to do a cube and a plane, then that like it's even looks even worse, right? So like that's kind of like the best. But yeah, it's like I don't like drawing down like a line because it's kind of like suggesting that one's smaller than the other, and it's better to think of them as kind of like the same size because they're both in dimension. But I mean the basis is infinite. Uh, mhm.
When we define like even odd, like, when did we talk about like pre-logs?
Oh, I threw that in the. I was just saying at the beginning that I just want to consider functions that are periodic.
So is it like or just
Well, I mean, right, like I'm not just being periodic anywhere for the orthogonality of even with odd, right? Like the only thing that I'm missing there is that you can integrate them, right? Um, that you can integrate them, and yeah, that's the only thing that is being used here. Is that like being periodic does have certain, it does make your life easier in like 10 minutes, but not right now.
So far, we haven't.
So far, there's nothing about, right. So,
That is true.
yes, as long as the integrals make sense, everything is defined where like you can integrate, then you're good to go. Yeah, like this, because this only used, right, like to say that this was to say that this was zero, you just have to say that this was odd. I mean, I guess you did have to choose a kind of like a symmetric interval, where like for like it to come up nicely. But that has nothing to do with the periodicity result. Like for example, you could have done it from negative infinity to infinity, but there then you do have to make assumptions about that whenever you multiply them, then the product continues to be integrable and things like that. Because with the proper integral, you have all these like issues of convergence, which makes your life complicated. So you do have to have like more extra calculus conditions. But yeah, if all those things were in place, then this just only uses the fact that the interval is symmetric. I'll just make a remark here that it doesn't use periodicity, doesn't use being periodic. Is that okay? Any other questions so far so good? How are we doing? And then claim. This is an also interesting claim. Again, I'm surprised when I think about it, I'm surprised that you never give this as a Calc 1 problem, that the derivative of an odd function is even. Okay, so claim 3. If f of x is odd, then f prime of x is an even function. I mean, that's kind of like a simple exercise. If you just do the definition of derivative, you play with the formula and you find that makes that have to be even, and vice versa also works, right? If the function can be even, the derivative can be odd. So like the derivative changes odd into even or even into odd. Likewise. I mean, I won't do that one because it's like a fun calc exercise. Actually, I mean, full disclosure, when I was on the train, I was, ask ChatGPT for the proof, just for fun, to see what it would give. And it gave that, I mean, actually gave two proofs. One with the limit definition and just like the other with the chain rule. So, I found like the chain rule one is more confusing because just like of the composition, like the form, like actually the limit definition, I feel like this is one where like, it's a bit nicer to kind of like do it from the limit definition. Likewise, like if g of x is even, then g prime of x is odd. So why am I bringing this up? Because now, what I'll do, here's what I can do next. Now that I have set up all of this in place, then you can think of the derivative, right? So these are like the odd periodic functions. It is the even periodic functions. And so because of what we just said, you can think of the derivative as a linear map, right? That takes it takes a function with derivative. Okay. And the reason why I'm doing it this way is that so that you kind of like think of the starting point and the ending point as being different spaces so that it looks more closer in analogy with the rectangular matrix, right? Because I could, of course, like you could have taken all the periodic functions here and here, right? Because like the derivative from a periodic function is periodic, but then the starting point and the ending point, they would have been the same space. So it would have looked more like a square matrix, right? So I wanted to frame it in a way where like this, you kind of like think of this more like being like some sort of like Rn and this as an Rm, so that it's more like closer to like a rectangular matrix. That's why I'm doing it this way. So this is more like, think of this as like kind of like Rn and then like an Rm, meaning that because like the space that where beginnings and ends are not the same, then like it is closer to what a rectangular matrix is instead of like a square matrix. Okay. So by choosing these domains, by choosing this, so D behaves more like a rectangular matrix. Because of my choice of domain. Given my choice of domain. Yeah. Well, that means that well that right, like that means that like the current like the null, there's no null space in this case, right? Because what is like the null, right, but that also is sensitive to the domain actually, right? Because what would be the null space of the derivative is all the vectors, right? They're the vectors or like the functions such that the matrix times a vector equals 0, right? But that means that the derivative has to be 0, right? So it's a constant function, but constant functions are not odd, right? They're even. So there's no null space given this. I mean, the null space is trivial. That's what I'm trying, because of how you chose it. If you had chosen the derivative going from all the periodic functions into all the periodic functions or something like that, then the null space would have contained the constant functions. But it does depend on the definition. You see, so f is constant, but constants are even. So f is even. So because of the choice of domain, like then there's no null space. So no, so not in the domain. So because of the choice of domain, it is trivial, the null space. Yeah. I mean, you could have like because everyone there would not have been anything wrong with like just doing the derivative from even into odds, and then that null space would have consisted of like a constant one. Right. Yeah. So it does depend on how you set it up. Or the constant function equal to 0, because that's the only 0 is odd and even at the same time, right?
For now, for the operation B, in considering that those spaces just ought to go from.
Right, yeah.
So why does the?
Oh, because what is like the reason why I'm trying to make the analogy, because what is an n by n matrix, right? Is it's from Rn into Rn, right? So that the domain and the target space are the same space, right? But here you start in odd and you end in even, so they're not the beginning and where you start and where you end are different, So that's the only reason why I'm doing it this way, so that it kind of like suggests more that it's more like rectangular because it doesn't begin and end in the same places, right? Like for example, yeah, if you had thought about the derivatives as being like all periodic, right? All periodic functions and all periodic functions, right? Then from this domain, it is more like a square matrix because it begins and ends on the same domain. But I wanted to do it kind of more like with the analogy of being rectangular, so that it's kind of like an infinite dimensional version of an SVD for a rectangular matrix. That's kind of what I'm going at for it. Because then, because if you wanted to do an SPT, right, what do you need to do? You need to do the eigenvalues and eigenvectors of A transpose A or A transpose, right? If you remember for SVD, for the SVD decomposition for a matrix, right? What does the SVD says? It says that A is like U sigma, right? V transpose, right? And you like the matrices U and V are formed from that you need like eigenvalues and eigenvectors or of eigenvalues and eigenvectors of A transpose and A transpose A, right? That's how you build the SVD decomposition. And so kind of like what I'm trying to suggest is that you should go from D as being like a matrix A, right? So what you actually need in this formula, then that begs the question of what should be the transpose of the derivative, right? Then you have to ask what is the transpose of the derivative of a derivative, right? So what is D transpose? So like once you have D transpose, you can try to analyze this problem and see what it should be. So question is what should D transpose be? Once you have that, then you can kind of like set up the problem for SVD. Then the thing, when you think about the transpose, right, the basic definition that you are given is like, oh, you change rows with columns, right? But that's not the correct definition of the transpose, right? Or not that elegant definition, right? Like what is the elegant definition of the transpose of a matrix? So you should actually start by asking what is A transpose. So again, if you think of Rn, and here you have Rm, if you have a vector B, right, like remember A is m by n, but like that kind of flips that if A is m by n, then it starts on the Rn, like it goes backwards. So here's A times B. Right, and similarly, if you have a vector U on this side, then A transpose, A transpose is n by n. So it goes in the other way, right? And this should be A transpose U. So the transpose is defined in such a way that when you choose two vectors U and V, that these two dot products coincide. That's the definition of a transpose. So the definition of the transpose, A transpose is a matrix for which you know, V dot A transpose U equals AV dot U. So that's not like the actual definition of the formula. Like that's like the defining property of the transpose. For any vectors U and V is for any vectors U and V. And then you can show that that kind of agrees with the operation of changing the rows out. But kind of like the idea from the dot product perspective is that the transpose is whatever. What this is saying is that you can move, like what this is saying is that you can move. You had the A in one of the factors. It's not a scalar, right? It's a matrix. So the transpose is defined so that you can move it to the other factor, but the price of moving it to the other factor is to transpose it, right? Like, so you can move that's what the transpose means, that you can move the matrix around as long as they transpose, right? Uh, so you can you can swap the factor in which the matrix appears. So you can you can move A to the other factor by transposing it. As long as you transpose. And that's like a very elegant definition. And the cool thing is that that kind of like has like an immediate definition, like an analog definition in any place, as long as you have a notion of dot product. Because then you take this as your working definition or like the dot product. So you kind of like do the same picture here. You can do the same picture here, but with derivatives. But now it would be the derivative. Well, I could have, I guess I could have erased everything. Like I'm not getting too much from this picture. So you had the derivative here. These were like the odd functions. These were like the even functions. Right. So the transpose should go, whatever the transpose of the derivative is, it should go backwards. And then you have here a function which is odd. Here you have an odd function. This gives you f prime of x, right? And here you have a function g, which is even, g of x, I guess. And this is g, like derivative transpose of g. I don't know what that is. That's what we're going to try to find out. Right, so I don't know what that is. It's going to be it's supposed to be an odd function, but besides that, we don't know what that is. But the definition should be the same. So the transpose is defined in exactly the same way. So the definition of the transpose, so the transpose is defined by enforcing the following equation. So what you want is the inner product. Again, I'll use kind of like Dirac notation for that. So what you want is something like this. So it kind of like this makes it nicer, like, because it's saying, well, you can move the D to the other side, to the other function, as long as I'm close to whatever. Is that okay, so for a second? Right, if someone checked out the homework problem, I kind of like, that's why I put it there, but I mean, it's still next week, but I thought it was, it still work. I mean, it's nice to discuss it together because it's like a very useful idea. But okay, so, but we do know what is each of these sides. So this is like the integral from negative pi to pi of the transpose of g of x, which whatever that is, times f of x dx. And this is the integral from negative pi to pi of g of x, f prime of x dx. Right. And then, well, let me touch this down here. Like, let me decide that you want, what should we define this transpose G as so that this kind of like marks. But so you see, if you compare, if you compare this integral, like I don't have an idea what this is, but at least I do know that there's just f here. There's no derivative of on f, right? Here's f without derivatives, but here f does have a derivative, right? So is there a way to rewrite this integral so the derivative is moved to the other function? How how can you move a derivative to the other factor of an integral? I think there's nothing to move. Yeah, because you're going to be there that. So I want to write start with I in 3 in 5. Well, it's not like the grain of both sides, but is I integration by yeah, what is if you think about what is it? I don't know if they tell you that, like, what is integration by parts? U dv equals UV minus V du, right? That moves the derivative to the other side. That's how you should think about integration by parts. Like, it's a formula for moving the derivative, which is like, it's crazy. Like, if you're not told that it's listening, but when integration by parts really is like, I have the derivative in one factor of the function, let me swap it to the other factor. So if you do integration by parts here, right? If you do integration by parts, this gives you, that gives you f of x times g of x evaluated at negative pi minus the integral from negative pi to pi of g prime of x times f of x dx. That's how integration by parts is. That's a big man. Like, integration by parts is definitely like one of the most important for just precisely for this type of fix because it allows you to move derivatives to the other side. But then, what is this? If you have a boundary term, this is what this is called this, like, like, so what is the value of this boundary term given the assumption of the function that they were periodic, right? So what is what is this boundary? What does that give you? It gives you it's just, right. It's zero because f right. It's f of pi times g of pi minus f of negative pi times g of negative pi. So this one gives zero because of the periodicity, right? Because the functions have so here I'm using the periodic condition. This is actually the same, like if you ever take calculus of variations, how they like, derive the Euler Lagrange equation. I mean, like similar trick to how they derive Euler Lagrange equation. There's like you can have an integration of parts. There's like a boundary term that vanishes if you have like a boundary conditions that gives infinity. And then and then you just get this. Okay, so just by comparison, right? Just putting all of this together, this should be the same as this. So what you want is to do these two integrals to be the same, and I will write it in a way that's a little bit more suggestive. So I'll write it like this. I'll put the minus in front of the G prime. Oh, sorry, there's no F prime here anymore. Okay, so you want those two integrals to be the same all the time. They have the same f, right? The f's are already the same. So the easiest way in the world, to guarantee that these two would be the same is just to force these to be the same as this. So and that is actually the definition for the transpose of the derivative. So the transpose of the derivative is minus the derivative. Like that's all that there is. So it's kind of like a weird definition if you think about it just as swapping rows with columns, it wouldn't make sense because when you swap rows with columns, you never negate anything. But you have to think about it from the integration by part, from the dot product definition. So d transpose of G is just minus d of G, so minus the derivative of G with respect to X. And that is the correct definition for the transpose of the derivative. Is that making sense? And again, you have to think about it. So it doesn't correspond to swapping rows with columns in any sense of the word. That wouldn't be necessarily. There's no change of signs there that can be thought about it in that perspective.
So essentially, with overall, we essentially expanded our definition of dot products to be functional. And then we did some heuristics and resolved it. For the normal definition of the dot product, matrices have some property for
Right.
For
The transport.
transport.
Yes.
And we want to ask for this extended definition of functions. Do functions behaving like matrices have similar transport properties given these properties?
Well, right, like the derivative in this analogy is what's behaving as a matrix and a function as the vector, right? So, but yeah, like if you think of the derivative as a matrix, what would be the definition of the transpose, given that you know that the transpose with the dot product can be moved around? If you think of right, like if you think of and this is actually, if you think of the correct definition of the transpose as being this operation that allows you to swap the matrix from one factor to the other. Now that we have a dot product between functions, if you think of A as being the derivative, what does that entail? What does that mean for the derivative as a matrix? And that what is it to be?
So really, so far,
Mhm.
we just have extended the definition of dot product from dot to inner product.
Correct. Yes.
And all we're doing is taking different notations of different properties such as this.
Right.
And we're looking at from the lens of dot product
Exactly.
and then extending that.
Right. Yeah. And this is actually, but if you think about it, like, if someone had asked you, okay, I mean, it is natural to swap rows with columns. I'm not saying that seems artificial, right? Like, so it's like a natural definition of a transpose of a matrix. But if someone asks you, why is that useful? If you kind of like write the formula in this perspective, it kind of like makes it very clear why this is useful, because the dot product is like a very important property, right? So it's very useful being able to swap the factor in which the matrix appears. Like, that does seem like a very useful property to have. So, like, this is kind of like even in linear algebra and finite dimensions, like this is the correct definition of the transpose, because even in finite dimensions there are other dot products. You can define different dot products which are not the standard one, right? So you can like that definition that corresponds to that. But then, and then you kind of like you get rewarded in the end because what was the point? Okay, what was the point of the singular value decomposition? Like, just to go back to SVD, the idea is that if you did something like A, right? What did I say about A transpose A? I had said that, for example, had like non-negative eigenvalues, right? Like it had eigenvectors and non-negative eigenvalues, right? So if we made the right definition, this should have like a similar result here. That if you do D transpose times D, that should have non-negative eigenvalues. That's what you would expect, right? So you would expect, based on by analogy, so we would expect D transpose times D to have non-negative eigenvalues. Right, but then, but right, how would you solve, like, what does it mean to have like an eigenvalue and eigenvector here? Like, it just means that you have a function for which this happens, right? Like that would be an eigenvector for this thing. But what is this? That this is, and now, I mean, hopefully everyone took like differential equations, like, or maybe you haven't, but it's kind of like, well, what is this? This was the derivative with respect to x. This was the derivative with respect to x of f equals lambda times f, right? So this is the second derivative. And that's an ODE of second order, which is linear, which you know how to solve from, like, Is that Hooke's law, actually? I mean, like, basically, I mean, if you have written this, like, yeah, it's kind of like Hooke's law, almost. Uh, so, like, the solutions to this, like, like, there's like all these ways from ODEs to solve them because they're linear. So it's a linear second order ODE. So if you remember like more, or if you haven't done it, you kind of like make a proposal for the solution, kind of like an to the NC or like NT or NS, kind of like a characteristic, and you get like this characteristic equation, This one's just like an eigenvalue, eigenvalue of a vector problem. And so, and like just to kind of like make it more concrete, imagine like you had tried to, imagine you had tried like a proposal which is like f of x equals sine of kx. Why sine? Because it has to be odd, right? Or would be like f would be odd. And so you can just try to do it for like an odd function. So here at okay. Then you would get that f prime equals k cosine of kx, and then f double prime equals minus k squared cosine of kx, right? And so if you plug it back into the ODE, you get minus of minus k squared cosine of kx equals lambda. Oh, sorry, right. Thank you. Yes. Like you mean this one? Yeah, thanks. Um, lambda times sine of kx. Right, so it's the same function, sine of kx on both sides, and the minus minus cancel, so lambda had to be k squared, right? So the eigenvalues are just like k squared, and the fact that the function had to be periodic forces the k to be an integer, actually. Positive because if you use negative integers, because sine is odd, like doesn't like give you anything new. And so here, because k is periodic, since sine of kx has to have period 2 pi, that's called like a boundary condition, right? Like f of then k, like, because here, like, it could have been any number, real number, right? So it's continued. But when you impose a boundary condition, like you discretize it or like you quantize it, right? That's how the physics called this, right? Like you just like that's the nice thing of having like finite intervals, like like it's kind of like the harmonic calculator. So then k becomes an integer. A positive, you can take a positive integer again, because if it were negative, like like that, like just parallel to, well, let's just say an integer. That's all that I need from here. Hmm? Um, no, not negative, right? Not negative. I mean, you can kind of like, right? You can kind of kill off the k equals 0 because the kernel, right? Like the null space is trivial, but all that I wanted to know was that they were not. All that I'm saying is that this shows me that this was a good definition for the transpose, because it has this nice property that if you do T transpose times D, the eigenvalues need to be non-negative, right? And that's kind of like one of like the nice things about the singular values. Uh, of the SVD decomposition, that they're always negative. So that gives you the singular values of the derivative. The singular values of the derivative are just the square root of the integers, of the positive integers, right? So the singular values of D. Sorry? Okay, let's go back. So we're saying, oh, here's what happened. So I start with just sign of kx, right? Let's say like my proposal is sign of kx by the chain rule. I get a k. When you do it again, you get another k, but then cos derivative of cosine is minus, right? So that's why I pick up minus k squared. And then you plug it back into the differential equation. Oh, that's what I did here. But the minus is canceled, and then you just get the lambda has to be k squared, right? If because sine is odd, right? I think it start with like odd spaces, right? So sine is odd. That's why I'm saying that sine of minus kx minus sine of kx. So it doesn't matter. That's why you don't need to use negative values for k. But
why don't you start that?
oh, because at the very beginning we started with the assumption that the function for period pi. At the beginning of the class, all of this was under the assumption that the functions were periodic. That does get used if you look at the proof, because when we found that transpose, right, when we define the transpose, we did use the fact that the boundary term, we did use that when you do integration by parts, that this should be zero. But to use that this should be zero, you do have to use the fact that at the endpoints we have the same value. So like it was used explicitly at some point. And so that tells you that the singular values, the singular values of the are, sigma k equals root of k for k a positive integer. And then you kind of like get the Fourier series, right? Because like the eigenvectors are signs, like the eigenvectors of D transpose D, they're just signs of different frequencies, and the eigenvectors of D transposes are the cosines. So, then the eigenvectors of D transpose D, they're just like sine of kx. Well, you can normalize them so that they are length 1, so you divide by 1 over root of pi. Those are the eigenvectors from these. So they're kind of like our analog of the P's, like the vectors V in this SVD, so they would make up the matrix for k positive. So they make up the matrix V. If you wanted to think about representing them as a matrix in the singular value decomposition. And then the eigenvectors of, you can also find this pretty easily, of the transpose are like the cosines. So it's, but here the k can start like greater or equal to 0. Oh, well, yes, like. So they make up the matrix U. And then, I mean, I won't go through the details, but it's kind of like a similar idea. Then you can even ask for the pseudo inverse, the pseudo inverse of the derivative. And what would be the pseudo inverse of the derivative? It should be something that reverses the derivative. So you would think, oh, it should be the integral. And then, yeah, you can show that it's actually the integral. You just have to subtract kind of like the average value. It's kind of like a shifted integration, like, I'll write the formula, but you can kind of, we kind of like talked about like, so, I'll kind of like write it in scare quotes, there's kind of like a singular value decomposition for the derivative, and then there would be kind of like a value, a pseudo inverse for the derivative, right? Which is like, what was it? It was V sigma plus U. transpose, if I'm not mistaken. Again, all of that is both, because then you do have to be careful there. But the idea is that the pseudo inverse would be, yeah, it's kind of like basically the way I set it up, it would be like a definite integral. Let's see. Where G var is just like the average value.
And this is like an infinite. Like.
Right. If you thought about them as matrices, they would be infinite dimensional, right? That's why I'm putting them in character. But I'm just saying, like, the analogy is more or less formally correct, like almost it kind of works nicely. I'll ask you what I'll do is now I have one in the problem for another example. This one is related to the kernel method machine learning. So I'll do now like an example with the kernel. But it's not like the same idea. You apply like LNCD to that, and then you can have the variance and all this other stuff. So it's kind of like all that I'm trying to kind of like sell is the idea that there's so many notions from finite dimensions that you can extend to infinite dimensions, where if you're just looking to go with the flow, it's kind of like more like work. Of course, you have to really some technicalities so that it all is completely correct. But it's kind of like a very cool idea. Like, but yeah, I'll give you a more concrete example on that. I'll add some problems to that on the notes, like where it's kind of like these integral operators. That's how they're called, and that's related to integrating like a kernel function. So you'll see, because like you want to talk about kernels probably at some point in the class. So this is kind of like a good segue. I don't think it's anything I think I've done some useful things.
So essentially, if um, if cosine of x is sine of the eigen of your derivative.
Right.
So you can represent every derivative as like some scaling matrix that scales out cosine.
Right. And that's kind of like the Fourier analysis, right? Because in Fourier analysis, you can break up, like, for example, an odd function. You could break up an odd function as a infinite sum of cosines of different frequencies, right? And then what this is just saying is that in that basis or in that coordinate system, the derivative acts like as a rescaling in the cosine direction, so it's kind of like this is kind of like the eigenvectors that diagonalize. I mean, quote diagonalizes like the derivative. But yeah, so it's kind of like with respect to the axis of in the function space, there are a bunch of different bases with respect to the axes that are made out of like the sines of the cosines. So kind of like the derivative is mostly kind of like a rescaling by these frequencies, like, or that's the square root of the direction. So it's kind of like, but it's not as close as you could ask for if you were looking for like a generalization of the FPD, more or less what FPD says. But of course, with some technicalities that you need to go over. But yeah, I thought like it was at least I should do this example so that you see kind of like that this is like a very useful idea. And then next week I'll start telling you about probability theory and how the FPD also helps you with that, and one way to compare probability distributions, like which is also used for machine learning and other cases as well. But yeah, let's make here if someone has more questions and I can keep answering them. Happy to stay. Yeah, I think this looks a lot better now that I fixed the projector. Yeah, like the quality with the